MNIST dataset, you know it already. We have a standard handwritten digits. Okay, they are all the digits have been written by human hand, manually written. Now we are going to see that if computer generate those digits, how it generates. Okay, with some sense of creativity. So that's what we are going to see. Already I ran this, but anyhow, I wanted to run in front of you so that you can see that how the computer generated text looks like. So at every stage, you could see the improvement. Initial few iterations, okay, initial few iterations, you could see you don't understand any patterns at all. So the display has written in such a way that, okay, it is going to produce the output or display the output after every 10 iterations. Sorry, every 500 iterations. Can you see here? There is a condition has been given. Iteration mod 500. Okay, it's a multiples of 500. I wanted to display because I don't want to display the output at every iterations, because the improvement will happen only after 500 iterations, at least minimum 500 iterations. Then only you can see some considerable changes in the output. Iteration by iteration, we cannot see any difference. So I want to totally I ran this for 6000 epoch. Look at this 6000 epoch, but I wanted to see the result at every 500 epochs. You could see that initial few iterations, its generator model, it try to produce some digits, but it's not perfect, right? As the iteration progresses, can you see as the iteration progresses? What I have shown earlier is at 500 epoch. Now the next display it will show at 1000 epoch. Can you see at 1000 epoch, it tried to produce some digits based on the database. What is the database? MNIST database I provided. At 1500, let us see. At 1500 epoch. First, if you see the application, it will set the curiosity for you, right? How the model produces this. So first I wanted to show the application. Look at some few digits are okay. It's now it looks like a 3. This looks like a 0. This looks like a 4 or 9. But it's not so perfect. Next is 2000 epoch. So as the iteration progresses, you can see, okay, your GAN is going to produce something like the computer generated text. Something looks like your database image. Okay. Suppose one of the image, if I take randomly and I'm going to ask you, okay, whether this is a human written, whether this is a human written 8 or it is a GAN generated picture, of course we cannot say. In fact, this is a GAN generated 8. Again, this is a GAN generated 9, GAN generated 3, GAN generated pattern 4, all created. But the beauty of GAN is we don't want to recreate the original. Then you may not appreciate the GAN. If you wanted to have the creativity, right? If you wanted to have the creativity, say for example, at say 20,000 iteration, your model is going to bring exactly the same kind of images. There's no interest about it, right? If you need more creativity, right? Better you premature stop. You stop little premature. Instead of 20,000, you stop somewhere at 15,000. At a premature stop, you may get some kind of a creativity. Whether you need that or not, it depends upon your context. Okay. Now let me run few more iterations. Let me bring it bit still closer to the training images or little away from the training images. So same thing we have discussed in the text large language model also in the temperature, right? Temperature setting. If I set the temperature setting very high, what happens? High randomness, isn't it? High randomness. High randomness is required for creativity kind of output. And low randomness, if you set the temperature value like a 0.1, 0.2, it's a low randomness. What kind of application low randomness is needed? Chatbot, question answering. Imagine I'm using it for some medical question answer. Okay, it's like some healthcare database. For a medical question answering, I cannot use the creativity, right? I have to give a precise answer. Even Bard went to disaster. First time when they implemented in the medical question answer, it became a very big failure because the number of training example was not sufficient. So wherever the creativity is needed, there, if I'm asked the model to write a story, okay, write a story based on so and so character, there I need a creativity. There I can set a temperature scaling high. Some application like a chatbot or a translation, one language to another language conversion, where I need a precise answer, I need to set my temperature to a smaller value. So similarly for the images also, you can have a control in terms of at what level you train it. Okay. So what is mean by at what level you train it? Okay, you will shortly, by the end of the session, you will understand. So we can have our control. What level you want to have a GAN, like a premature stop, or with more a number of iterations you wanted to stop at all. We can have our own control. This is already, I ran it for 6000 epoch. Okay. But once again, I wanted to run it. Okay, let it run in the background. At least I first at the end of the 500 epoch, if you wanted to see the result. Okay, train GAN. So it starts afresh. Okay, so let it run in the background. Standalone generator, we are going to understand how the architecture is. Standalone discriminator, we are going to learn a standalone generator, standalone discriminator. Number one, this is number two. Number three, how I tie these together, how I combine these two guys. Okay, to name this as a GAN. That is the third component. When you tie this together, okay, there is some method is there, because which order they have to learn, right? So first discriminator has to train, and then I should freeze this guy. Then I should enable the weight update process for the generator, right? So whatever the theoretically we have learned the ideas, I have to put it in the form of a coding. Okay. So this is the third piece. Third piece, how I bring these two guys together. So I don't want to rush up all these three in another 20-25 minutes. So let me focus on the two components. Okay. So the first two components. Okay, this itself, it will considerably take another 15-20 minutes. So towards the end, if I rush up this, you may not understand which order I tie up this, because this is a very crucial part. Once you understand this, extending this idea to other genre of images, it's very simple. You little bit tweak around this code, play around with this code. That is very simple and straightforward. Okay. So tomorrow agenda is like I'm going to use the same GAN for color image generations. So here we are producing single plane output, for color 3 plane output. Okay. So not necessarily you need to use only the built-in images, even how you can use your own set of images. Okay. Even you can do some interesting experimentation. You have a collection of, that is an assignment task related to this. You have a collection of your own pictures. Okay. Like at 10 years, at 15 years, at 18 years, 20 years, 25 years. Assume that you have a collection of 50 images. Okay. And you ask the GAN to synthetically produce the photograph, something similar to you. It's a very interesting task. Okay, you can do that. So how you can modify the code for custom data set, that also I'm going to teach in the final session, tomorrow session. So two agenda. First of all, how you have to modify the code for color pictures. Okay. Once you learn that trick for built-in images, easily you can extend that idea for your own database. That means you are reading the image part alone is different. That means this design and all, it's going to be the same. Of course, according to the size of your photograph, you have to modify the generator. But otherwise, the same core idea of the GAN we are going to use. So let us focus our attention on standalone generator and standalone discriminators. Discriminator is very simple for you. It is a binary classifier. It's not a big deal. But of course, generator component, even though you have seen the generator component in the context of unit, okay, here how I have designed the generator to the context of the GAN architecture, almost same only, but the initial few steps could be quite new for you. Let us see how I build this generator. Because as per the paper, okay, the latent space, right? The latent space means they create a two-dimensional matrix from the one-dimensional latent vector. Latent vector means 1D vector. Look at the input size. The input size is, we start with 1 cross 100 randomly generated one-dimensional vector. So this randomly generated one-dimensional vector value is called as, in the paper they have mentioned this as a latent space. So maybe you can write it like a vertical, okay, 100 values. What I do in the very first step, I connect these values. Okay, these values are act as my random values, right? Random numerical values. I'm going to connect this with using a dense layer. You know what is dense layer? Like a fully connected layer. All these 100 inputs are connected to a size of 7 into 7 into 128. Why particularly 7 into 7 into 128? You'll come to know the reason why. To understand why we are designing like this, I have made it like 7 into 7 into 128, but otherwise you can directly specify 6272 neurons. Why 6272 neurons? Because I'm going to reshape this guy. Afterwards, look at the way I reshape this one dimensional. I'm going to reshape it like 7 cross 7 matrix of how many filters? 128. So 7 into 7 into 128, you will get 6272. So that 6272 you can directly pass here. No need to specify 7 cross 7 cross 128. So your randomly generated 100 values. First, it is going to map down to 6272 neurons. Why this mapping? As a linear combination. Map this and then you reshape to 7 cross 7 by 128. Why particularly 7 cross 7? Because what is my objective here? What domain image I'm going to generate? Image similar to MNIST dataset, right? Image similar to MNIST dataset, 28 cross 28. So when I do upsampling, see, I should not use the word upsampling. Superficially, I can use it, but to be very precisely, convolution 2D transpose. Can you see convolution 2D transpose? Whenever you do the convolution 2D transpose with the stride 2, what happens? It will double the size. So we have one exclusive exercise dedicated to understand the concept of convolution 2D. In case if you forgot, revisit that exercise, revisit that recordings, have an understanding in case if you forgot the process. So the 7 cross 7 cross 128 will upscale to 14 cross 14. Next stage when I use, it becomes 28 cross 28. But in the last layer, I should use one filter because I need to have only one response, isn't it? To have only one response. Look at this. In the last stage, I have used only one filter. Only one filter. Let's try to one. So better you execute this and see the summary. You'll understand the process. Okay. At every stage, of course, we do the batch normalization for the better convergence. and also the leaky relief we have used. Other than that, your regular design. In fact, here I have used relief. Okay. Anyhow, this is not a very difficult image, isn't it? Not a natural image. When in the next exercise, when I move to the natural images, I have used a leaky relief, but a leaky relief is the standard, the best practice standard. But you may ask, sir, why you have not used the leaky relief? Because it's not so complicated image. So I just use the relief itself. Tomorrow, the final notebook shared with you, lab 50 notebook, I have used the leaky relief. So let's see, it's again activation function you can directly define in the convolution layer itself, or you can separately define it. So let us understand the summary. Okay, you can understand the workflow. We start with the latent vector, one-dimensional vector of size 100, which is mapped onto the dense layer with 6272 neurons. After reshaping, you produce 7 by 7 128. So batch normalization is just it's scaling the values, and activation function is being applied renew. All the negative values are converted to 0. After convolution 2D transpose with stride 2, it's doubled the value, right? 7 cross 7 become 14 by 14, followed by batch normalization, activation. Once again, convolution 2D transpose, 14 by 14 converted to 28 by 20. Suppose if you wanted to produce a bigger size, double the size of it, 56 by 56, one more convolution 2D transposition. Still bigger, one more convolution. So whatever the size you wanted to achieve, okay, that many convolution 2D transpose you should use it. But of course, each and every layer you insert, it is like a time consuming process, computationally, it's expensive process. Okay. Like whatever the results we have got quickly for this MNIST data set, it may not be possible for the tomorrow color images. It may require a huge amount of time. So tomorrow at the beginning of the session itself, I will execute the training process. Okay. It will require the minimum half an hour or to 40 minutes. It depends upon what type of images you try. So I will run the training process in the background. Okay, we'll start our discussion and then finally we go and see the results. So it produces 28 by 28. And then next to two section, I keep the stride 1, okay, to gradually reduce the number of filters, but I have to maintain the size. Okay, so the last two stage you can see I have used the stride 1. It maintains the same size, but gradually reduce the number of filters. So 28 by 28 is maintained with 64 filters. Again, 28 by 28 is maintained with 32 filters. At this stage, finally, the last stage, I use only one filter. Okay, 28 by 28 by 1. This is what the final output. Because in the last layer, we wanted to keep all the values to be presented as the more normalized range of values 0 to 1, right? Sigmoid will skews all the value to 0 to 1. You may ask why the sigmoid is necessary. The reason is here anyhow I have not used leaky relief, but in the subsequently the best practice of GAN, leaky relief, right? Leaky relief we are going to use. Leaky relief even after the activation function, it has some negative values like minus 0.12, 0.015, some smaller values of a negative range. So the sigmoid activation function will convert these negative range values to 0 to 1. For that normalization purpose, this is used. So anyhow, we are not having any target here, right? Even the probability scores is treated as a normalized range of your pixel values. Your probability value itself treated something like a normalized range of the pixel values. So finally, we are going to consider this 28 cross 28 matrix, okay, which normalize the leaky relief response values as a normalized range of 0 to 1 pixel values. Like Traditionally, when we scale 0 to 255 gray levels, what happens when we scale 0 to 255 gray levels? In our earlier LAA foundation course, whenever we work with images, what we do, x train dot slash is equivalent to 255. We do what is the meaning of it? Each and every pixel we divide by 255. That means what? Your 0 to 255 grayscale, it is scaled to 0 to 1, right? So your sigmoidal response also can be treated as a scaled version of your gray level values. So don't think as a probability score here. At this context, you have to see it like a scaled version of the grayscale. That is a normalized version of the grayscale 0 to 1. So 1 being a brighter pixel, the value closer to 0 being the darker shades. So since you see the style of the coding is done as a functional design. So that is why finally I have to tie everything using the model API. See, I have used the model API. Finally, you have to define what is your input. Your input is coming from generator input. And what is the output? Don't get confused with the term X. So what is the general definition of your model? This is X comma Y. So usually X is the input, Y is the output. That is our general notation, right? But don't expect something here. In fact, your output is written as X. Only the variable is being named as X. But to the context of generator, it's what the output. Okay, just it's a variable. Maybe this term confuses you. Better you can rename this as a Y. Not an issue. Everywhere you just make it as a Y so that you will not get confused. So input comma Y. Okay. So your generator has been written as a separate block. Similarly, your discriminator is defined as a separate function. So you can run this and you can see the summary. You can understand the flow. Similarly, the discriminator block is very simple and straightforward. You know it. It's like a convolution based discriminator classification model. What your discriminator is going to get the input? It's going to get the input of 28 by 28 single plane image. It could be either image generated by your generator or with your original database, MNIST database, those initial digits. So whether this or the image generated by the generator, both are 28 by 28 by 1, isn't it? So as soon as it receives this input, it passes on to, see here it's a leaky ReLU has been used. In the generator side component also, we can use a leaky ReLU. But here only the discriminator side is being used. So whenever you use a leaky ReLU, we should use alpha factor, right, which controls that slope for the negative range, how you want it to compress. If you wanted to compress very narrow, you have to make the value very small. Okay. And if you put 0.5 means it's like a 45-degree line, same value. So better maintain this alpha value less than 0.5. Some better to use somewhere between 0.1 to 0.3 is very ideal. Okay. If you make the value very close to 0.5 means so no point in using the leaky ReLU because all the negative value minus 1.5 means output also minus 1.5. It won't compress the value. It's shorter range. See, it's your regular CNN based classifier, right? Your input is going to convolution 2D with the 32 filters. Next stage, 64 filters, 128 filters. The last stage, it finally produces 256. So since it is acting as a binary classifier, what it is going to do, I need to flatten the last CNN layer. I connect it directly to the, you may think, sir, why there is no hidden layer is required or not? Because I told you, right, initially your discriminator is going to learn. I don't want to build a very strong discriminator, right? I wanted to design a discriminator to be a very basic level discriminator. It's good enough to discriminate whether it is a digit or it is a noise. It's a linearly separable. A simple model is sufficient. I don't want to overfit this. So that is why a simple, even in the fully connected layer, there is no hidden layer. Directly I use the output layer with one neuron with activation sigmoid. So this is a discriminator block. So we have a standalone generator and we have a standalone discriminator block. Both are ready. And finally, these two guys need to be tied together to make it as a GAN. Okay. So how we prepare, how do we organize this? Which order I should call? Okay. That is the going to reflect the whole theoretical concepts what we have discussed. That is, it is given over here. Okay, this is the which order what need to be trained. Okay, that is being explained here. And finally, this portion, how do we prepare the input? How do we prepare the input and how to allocate the label? How to allocate the label? At what situation I should reverse the label? Reverse the labels. At certain time period, whatever the output produced by the generator, we present with the label 0, right? And then we reverse the label. After a certain time, we are going to, freeze, after freezing the discriminator, all the output produced by the generator, we should present with the label 1. So how do we do that in the coding? Okay, so which order we have to present? So that is what these two sections is going to define. So let us reserve these two cells for tomorrow's discussion. This block and this block. Okay, it's a very simple and straightforward. If you are very curious, just you go through the steps self-explanatory, but otherwise you can wait till tomorrow evening. We are going to understand this. So once we finish this, lab notebook 15 is very simple. Just according to the size of the input image, you should know where are the places you should change the dimensions. Once you learn the trick, okay, you can use this GAN architecture for any kind of images. You can have a database of a cartoon pictures. You can synthetically create a cartoon. But talking wise, it looks very easy. But remember, each one, it will consume several hours of training with a very sophisticated hardware. You should have a paid version of Colab or even higher version. So initially, to start with a smaller size, okay, don't think like a commercial ready images we cannot produce because of the limited infrastructure. At least you try to produce a small picture like 100 cross 100 color image of your own pictures. That is why I have given that as an assignment task related to this GAN. So the last exercise.